Login accepted.
All right, I believe that is my cue to get started. Welcome, everyone. Good afternoon. Welcome to Software Architecture Foundation Styles and Patterns. This is the second part of our Fundamentals of Software Architecture book, which is a deep dive on all of these architecture styles. That's what I'm going to spend most of my time on today, are the styles versus the patterns, but I did want to make the differentiation of how we separated those two things. Patterns are things that can be applied on top of any kind of architectural style, whereas a style is a top-level description of a structure or a topology or a relationship of components. You can have composite architectures that mix styles, but you can only have one fundamental style, whereas you can have lots of different patterns. CQRS is a great example of a pattern in software architecture because you can implement CQRS, the Command Query Responsibility Segregation, on top of just about any one of these architectural styles. These are important to understand from an architect standpoint because these are the starting points when you're going to build a new solution. These styles are really the starting point for, given the set of architecture characteristics or non-functional requirements and what my problem domain looks like, one of these is probably the most suitable starting point. And one of the big things that differentiate these architecture styles, besides just the obvious structural differences in them, is how they react to what we called in our book, this is the entire first part of our book, which is called architecture characteristics. These are also called non-functional requirements or system quality attributes or cross-cutting requirements. These are all those things that are not your problem domain. So let's say that you've got a problem and you've decided, I'm going to write some software to solve this problem. And so you have a problem domain that you have requirements for, and you obviously have to design for that. What I'm talking about are all the other things that you have to design for: reliability, availability, performance, scalability, deployability, modularity, security, all the ilities of software architecture. This is what we call architecture characteristics. And when you think about the structural design part of software architecture, it's really the union of my domain and whatever design considerations I have to make for my domain and these architecture characteristics, because each of these styles is basically a predefined relationship of these architecture characteristics. A certain deployability model, a certain level of granularity is often imposed by an architecture style, and so that has a big impact. And one family of architecture characteristics I'll talk about a lot today are the ones that we refer to as the operational architecture characteristics. Those are things like performance, scalability, elasticity, availability, reliability, things that overlap with architectural design and operations and DevOps, and those really influence one style versus another. So the way I have these separated for the basis of this presentation is fundamentally between generic versus domain-specific architecture styles. You can create your own brand new architecture like nobody's ever built before, and I have two short examples of those just to show you what those would look like. But we are most interested, of course, in the generic ones because those are the ones that you can apply across a wide variety of problems. And I further separated those into technical partitioned versus domain partitioned architectures. And I'll talk a little bit more about that distinction in just a minute. But that's really about whether we separate the architecture based on technical capabilities or has it been influenced by domain-driven design, and do we separate the architecture by domains or workflows instead. Then the third classification I have here is the number of quanta, whereas a quantum of 1 means it is a monolithic architecture, meaning that it is typically one code base deployed as a single unit typically with a single large relational database as well. So typically deployed, and the engineering practices treated as one big thing, versus a distributed architecture which may be created and deployed in pieces. So microservices, example of a distributed architecture. And so that's the final separation here. So let's talk about these styles. And I'm only going to briefly talk about the distinguishing characteristics, and I will give you a scorecard for each of these. But what I want to focus on is the philosophy behind why that architecture style exists, because that's what you need to know as an architect to know, is it safe to make a hybrid out of this and bend it a bit, or am I fundamentally breaking the spirit of this architecture? And that, I have an example of that right away. So the first one I talk about here is the traditional layered architecture. The presentation layer, business layer, persistence, and database layer. This is the default architecture style in many organizations. When I go in and ask them, what kind of architecture style are you using? And they say, what is an architecture style? I know that it's this architecture. This is so common, in fact, that many organizations seat their workers based on this architecture, putting all the presentation people in one part, all the developers in another part, and all the database people in another part, because it seems like a natural partitioning. One of the characteristics of this kind of architecture, and one of the purposes behind these layers, is separation of concerns. And typically this architecture is each of these layers is closed, meaning that it only accepts requests from the layer directly above it. And this is part of that separation of concerns, because one of the benefits here, of course, is I can go in and make changes to the persistence layer to change how persistence works, and I only risk breaking the immediately adjacent layers. I don't have to worry about breaking the entire thing, which is kind of nice. And so the philosophy behind this architecture is really about separation of concerns. And there are lots of different variations of this architecture. The one on the left there would be a typical desktop application, which has a separate database, but then the main layers of the application are all together in a desktop application. The one in the middle is a typical three-tier web application, where you have an application server of some kind, a database, and then a presentation tier. And then the one on the right is typical of an embedded system or mobile device, where all the things are on one place, but still separated technically by layers. Now, one of the things that you have to understand about the philosophy of an architecture is, when is it okay to let people bend it a little bit? And so what happens in the layered architecture if some team comes to you, like the reporting team, and says, hey, you know, it's taking too long for requests to make it all the way through your layers. We need direct access from the presentation layer to the database. Is it okay if we do that? Well, your answer as an architect has to take into account, well, is that going to fundamentally damage my architecture? And in fact, now it will absolutely. Because if you wire the presentation layer to the database, you can just set fire to all those layers in between, because they're now meaningless. Changes to the database will have to be reflected in the presentation layer, and you've basically broken all of your separation of concerns. So you probably should say no to that. But how do you prevent them from doing it? What if you're in an organization where it's better to ask forgiveness than permission? Well, one of your other jobs as an architect is governance. Once you've created a design, how do you maintain that design? And this is the realm of my 2 books ago, Building Evolutionary Architectures, and the idea of architectural fitness functions. And here's an example of one, written in a tool for Java called ArcUnit, that allows you as an architect to define rules about what layers can talk to one another or not. So you see the first test there says no classes that reside in a package service should access classes that reside in a package controller. This allows you to programmatically control governance and make sure that people don't cheat on your architectural style that you've created. ArcUnit is in the Java world. Here's a similar tool in the .NET world. And so there's a whole rich family of tools that allow you to automate some of these architectural governance tasks. But that's not the subject of this talk. So the big driver for the layered architecture now, even in this day and age, is simplicity and cost. Everybody understands one of these, and this is the simplest, cheapest thing to build. And so if you're living on venture capital fumes and you must get something out as quickly as possible before the money dries up, this is still a reasonably good architecture, although I'll talk about another monolith later that's a little bit more suited. One of the things that we wanted to do in the fundamentals book is to provide a kind of apples-to-apples scorecard between all these styles. And this is an example of one of those. I'll show one of these for each of my architectures. This chart of interesting architectural characteristics where 1 star is bad and 5 stars is good. And so here we have a layered architecture. Almost all of these are 1 stars, like deployability, elasticity, all of those are really poor. Overall cost, the 5 stars there, 5 stars means good, which means inexpensive, which is a little bit unintuitive, but we can't fix that now. So very inexpensive because it's easy to understand, and reasonably good from a performance standpoint, and simple is the main driver for a layered architecture. So let's talk about some more interesting architectures. Another monolithic architectural style, which is one that you start seeing everywhere once you start noticing this pattern, is the microkernel or plug-in architecture. And this has two fundamental kinds of components. The core system, which is the minimal functionality required to run the system, general business rules and logic, but no custom processing, and no real volatile code, so this should be all very stable code. And then plugins that drive the changes that occur within this ecosystem. So there's a difference between an architecture that supports plugins versus a microkernel. And it really depends on how much responsibility there is in the core. One of the only really pure microkernels that is in common use is Eclipse. Because Eclipse with no plugins, I think, can barely open and save a text file, and that's it. All the other behavior is driven by plugins. Whereas a browser is functional without any plugins present. And so that's one of the defining characteristics of a microkernel. It basically does nothing if there are no plugins present. But this is also a really common pattern for business solutions as well. For example, let's say that you have an insurance company that needs to have rules for all 50 states. If you're familiar with the template method design pattern, this is basically a way to implement that in architecture, where you have the core things that we need to do for insurance, but then there are customizations for each state potentially. You can model all of these with plugins, and this makes it easy to move things in and out. Another common microkernel is something like a linter or a validation tool. Notice that just having a tool that can read source files and parse them is not that useful, but then you plug in things that you want to check, and it becomes a lot more useful. The thing that really defines the complexity of this architecture is how complicated are the contracts. And if you'll notice, most plug-in architectures, and in fact most microkernels, try to make that a one-way conversation with the plug-in to the core and not let the plugins talk to each other. Because if you do, now you're into OSGI and transitive dependency management and all the dependency graph that goes with all that. And if you've ever tried to install something in Eclipse and wrestled with it, you know exactly where you are if you let the contracts start talking to one another, because now you're dealing with versions and other stuff. So this is a really good example of an architecture that's really well suited if you have a problem domain that is in this shape. If you have something that's a core system and then you need to customize it, this is great for customizability. So pretty good for modularity and simplicity. This one is still pretty easy to understand because it's one thing and it's pretty easy to understand how the pieces fit together. Although if you've ever done any real work in Eclipse, you can see how complex some of the things around a complex microkernel can be. And as you can see, because this is a single, typically deployed as a monolith, although nothing says those plugins couldn't be accessed through network protocols of some kind with the attendant trade-offs. So the deployability is kind of cooked into this architecture, so it's well understood. Some of the things like scalability are not great here, but the cost is still not high here. Some of these others are reasonably good numbers. And so this is a good, like I say, if you have something that requires customizability, and like I say, you start seeing this pattern everywhere. Enterprise service buses often have this pattern. And the BFF pattern for back-end for front-end, it's commonly used in microservices, is basically a microkernel pattern, so it's very common out in our world. There are two different event-driven architectures that I want to touch on briefly here. Now, events and messages and message queues are often used as a communication medium in higher order architectures like microservices, but you can build entire architectures just on top of messages and event queues, et cetera. And I sort of compare this to if you were, if you've seen a prefabricated house. That's a house that comes with the walls basically already put together with holes for the windows where you just kind of snap the windows in so they show up with walls and you nail them together and then put the roof on and you can build a house really fast. That's like microservices. Building an event-driven architecture is like going to the hardware store and getting lumber and nails and all the little pieces and building exactly what you want. Now in a prefabricated house, you've already got a bunch of things that you can take advantage of, like service meshes and templates and all that, but you have to build your house in a certain shape. If you create all the stuff from scratch, you can build any exotic shape you want. So this is a lower level way, and it allows extreme levels of customization. And this is still used even in the current day because these two architectures have the unique behavior of giving you good performance and scalability at the same time. And that's a really difficult combination to achieve. Microservices give you really good scale, but often suffer from performance for reasons I'll get into in a second. These, you can actually have good performance and scale if done correctly, but one of the two of these topologies gives you more opportunities for performance and scale, and I'll talk about which one of those in just a second. So there are two fundamental topologies here, a broker and a mediator topology. Let's talk about the broker first. In a broker topology, you have a message queue, you have an initiating event out in the world that causes something to happen, and you have event processors where code lives in this architecture. That event processor may pick up that message, do some sort of internal processing, and then may or may not post a message to another event channel, which may be listened to by one or more other event processors, which will pick it up and do processing on it. And our workflow basically bubbles around these series of event processors as time goes by. Choreography is the description for the workflow in this kind of broker architecture, where let's say that we have the initiating event is you move. I'm moving, changing address. So that message goes to the customer processor, which processes it, and then posts a message to a message queue that says, hey, is anyone interested in a change of address? Turns out both quote and claims are interested in a change of address, and so quote will pick that up and update its internal quote, and then post a message to, hey, is anyone interested in notification? Notification will pick that up and do a notification for our customer. In parallel, because this is all asynchronous, claims will also update claims and then post a message to anyone who's interested. It turns out both notification and adjustment are interested in that. This is choreography because while it was planned beforehand by an architect, there's no central coordinator here looking after error conditions and, did they all finish or not? You can build that, but there's nothing built into this architecture that automatically handles all of those details for you, which is why this is choreography. And so error handling can be a challenge in this architecture. There are lots of patterns that you can apply, like the workflow event handler pattern to handle errors in this architecture, but it's something you have to write yourself and customize. But what about evolving my workflow in this architecture? What if the commandment came down from the domain that we need to audit all claims updates? Well, evolution is super easy here. I just need to add a new listener to my message queue that's already there, and I'm all done. Unless I start swamping one of my pieces of infrastructure, this gives me an easy evolutionary path, which is nice. The mediator topology has the same building blocks that we saw before, with one important addition, this mediator thing in the middle here, right there, this mediator thing in the middle. That's where orchestration happens. Now, this is an architectural pattern, and there are lots and lots and lots and lots of implementations for this mediator. Apache Camel is an example of one of these. Spring Webflow is an example of one of these. Every enterprise service bus has a mediator built into it. BPEL engines, the business process execution language, and BPIM, the business process management tools, are all versions of mediators. And mediator is basically a tool that lets you coordinate other event processors and maybe do pseudo-transactional coordination and other sorts of fancy things like that for them. But notice that in this architecture, all the messages go through that mediator, and it dishes out work to the individual event processors, including the fact that none of the internal event processors ever communicate with each other. Messages always go back through the mediator if you need to communicate between those. But if you look at my workflow here, it's much easier to understand because now I have all of these things in place. I can change address and send that message to customer process and have that happen, and on until my workflow is done. I can do pseudo-transactional coordination. I have much easier error handling. This is orchestration, where that mediator is acting like the conductor for the orchestra and managing communication and error handling and workflow and all that other stuff. So error handling here is trivial. It's basically built into this architecture because we already have that orchestrator there looking after things. And in fact, a common pattern is to have that orchestrator go and do compensating transactions to roll things back if something, if you wanted to create pseudo-transactional behavior. But what about evolving a mediator? Well, now this is more complicated than a broker because now I have to make changes in two places. I have to update the mediator, and I have to add my new listener, because remember, all the important workflow has to go through that mediator. So the drivers for an event-driven architecture like this is certainly modularity and agility and fault tolerance. Performance and scalability and elasticity are definitely the big drivers for this. It supports both adaptability and evolvability. Adaptability is the ability to keep existing behavior and add more to it and continue to. Evolvability is the fundamentally changing how things work over time. Supports all of those very nicely. And here is our star chart rating. Notice this is a distributed architecture, not a monolithic architecture. And so really good numbers here for things like performance, scalability. Simplicity, however, has taken a big hit. These are very complex architectures. And in fact, I'll go back to the question I asked earlier. Of the two, broker or mediator, which one gives you higher potential for performance and scale? The broker, because of less coupling. But notice that it also brings with it lots more headaches, deadlocks, race conditions, but there are still reasons that you build broker-style architectures even today, even with all their complexity, because they do give you unique opportunities for performance and scale and the ability to really tune things to a fine degree. And you'll also notice that broker event-driven architectures are extremely decoupled, because that orchestrator basically forms a coupling point in your architecture, which is what slows it down and creates a bottleneck in terms of performance and scale. And if your goal in a highly decoupled architecture like microservices is to improve performance, then using broker-style events is a common way to do that, because you don't introduce extra coupling points, but you do introduce asynchronicity, which gives you the perception that things are moving much faster, whether they actually are or not. And so it is still somewhat common to build low-level event-driven systems, although these are mostly built on top of a cloud and similar environments now. But you can still build these from scratch if you have extreme uses or needs. I'm building one of those right now for high-scale payment processing. Back about 20 years ago, the thing that was all the rage was this thing that we ended up calling in the book orchestration-driven service-oriented architecture, which is a distributed architecture from the past. And the idea behind this was, this is an enterprise scope architecture that had a very specific service taxonomy. So remember I said earlier about this idea of technical versus domain partitioning? This architecture is as far as we will ever go down the technical partitioning route. Because when you look at a layered architecture with presentation, business rules, etc., this architecture took that and just went crazy with it. Because there are layers in this architecture, but each one of them has a very specific responsibility within this taxonomy. The business services here are completely abstract and are basically just inputs and outputs and contract formats. And so these are supposed to be the things we do as a business, the fundamental business activities that we undergo. You should be able to answer affirmatively, we are in the business of each one of the capabilities delivered by these business services. So these are coarse-grained and typically owned by business users or enterprise architects. These are completely abstract, which means there has to be some implementation somewhere. That's here. These are also coarse-grained, but at a different level of granularity than the ones at the business service level, because these are meant to be these little business Legos that you stitch together using that message bus for a big orchestrator in the middle. And if you look at many of the tools in this era, they had some really crazy ideas about building software where you didn't know what the transactionality of this code is going to be. Somebody later would use a deployment descriptor to assign how it's going to cooperate within transactions through the message bus. And so part of the goal, the philosophy in this architecture, this is when big companies were starting to merge together, and they were really frustrated because it seemed like they kept writing the same business code over and over again. So they said, we're going to write all that business code one last time in these ultra reusable enterprise services so that there will eventually come a day where we no longer have to write any code at this level in our architecture. All new solutions can just be pieced together with the orchestrator by putting the Lego blocks together in new, unique shapes. Setting aside for a moment how naive that is, because the universe kind of fights you on that, because your markets continue to change and evolve and you merge with other companies, but setting all that aside, that was the philosophy in this architecture. There was a place for things that you didn't want ultimate reuse for, application level services. Infrastructure services were things like logging and monitoring and that sort of stuff. In the middle of this whole thing was that enterprise service bus that glued all these different parts together. And part of the obsession in this architecture was around shared resources. And so this is a typical pattern in this architecture that you were instructed to look for, which I talked about in my keynote this morning. Let's say you're a big insurance division and you notice at some point, hey, wait a minute, these all have some aspect of customer in them. And what you were supposed to do, part of your job in this world, was to notice this and go, hey, well, what I should do is consolidate that into one customer service and just have all these other services point to that customer service. Now I have my ultimate reusable customer service that I can use anytime I need to deal with a customer. But of course, what we learned with this architecture is this is the secret to creating brittle architectures. Because if you build an entire architecture over the fine-grained reuse you were trying to achieve here, you change one thing and everything breaks. So getting these things up and running was a big undertaking, and you'd finally get the thing up and running and all the things talking to one another, and it's like, whew. And then somebody would say, okay, now we need to make a change to the catalog checkout page. It's like, oh man, really? We got to deal with that again? The good part of this architecture is really good heterogeneous interoperability. And this is why you still see things like enterprise service buses today. Those are immensely useful tools if you have the situation where I need integration hub, because I need to talk to a bunch of old systems and new systems and have them communicate with each other, and I need to orchestrate that communication between them. What is a mistake is allowing the enterprise service bus to become the center of your entire architecture. But the good thing about it, because it is an integration hub, is it gives you the highest level of integration architecture, protocol agnostic, heterogeneous interoperability. What does that mean? Protocol agnostic means I don't care about the protocol. Heterogeneous means I don't care about the platform. And interoperability means I can talk to it. Because the enterprise service bus is an integration hub, you don't really care about what the caller and the callee are in. It paves over all those differences for you very, very nicely. It is also very good at contract decoupling. Part of the service that Enterprise Service Bus is doing for you is mapping one contract to another pretty much invisibly as far as you're concerned. This is still a legitimate architectural component for integration architectures, and this is really, it was always its sweet spot, and this is where it's still used is in integration. And in fact, the drivers for using an enterprise service bus now are integration, and orchestration. And yes, I realize I have a integration on there twice. That is the real driver. And it scores really poorly on almost everything here. But you also have to realize that many of the things that we value now in architecture, which are represented on this scorecard, were things they didn't care about or didn't know about when this architecture was popular. So it's not surprising that this is not high up there. I want to talk briefly about a question we constantly get, which is about serverless architectures. I'm putting that in air quotes, because there are two different kind of patterns that we see in a serverless architecture. Serverless, of course, is somebody else's computer, somebody else's problem, deploying things, but there are two different common deployment topologies, two different patterns for this. And one of these is back-end as a service, which really came on strong in the early days of serverless and then it's kind of faded a little bit and now is having a big resurgence. Back-end as a service takes the traditional three-tier system like this and says, okay, well, let's move all the code that is in the middle here in the pet store server, let's move that into somewhere else, into Lambdas, and find an online database that can access our product catalog, and an API gateway that can do our routing and all that other stuff. A lot of the code, the coordination code that used to live up here in your middle tier has now moved up to the browser, and so this makes the browser a much more important component in this architecture. You see tools like Jamstack, JAM Stack, implement this and become pretty popular implementing this topology. The other, of course, is functions as a service using Lambdas and the wide and widening variety of capabilities that all of your cloud vendors are providing for you. And they are going to continue to provide those things for you as time goes on. And so there are obvious drivers for serverless, which is the lack of apparent infrastructure and really fast spin up, et cetera. But we don't really consider this an architectural style yet. This is a deployment pattern. And the reason I say that is because a bunch of the different architectural styles we talk about can be implemented on serverless deployments. And so there's nothing magical about a serverless architecture. It's just an architecture with different kinds of deployment constraints and capabilities. And I believe that the major vendors are going to continue pouring money into the capabilities of these cloud environments, because I believe that it is Jeff Bezos' greatest wish to eventually be able to charge you a microtransaction for every method call you make. That is the ultimate dream if you're a cloud vendor, is that every method call is a little chink in my piggy bank. And so they're going to keep building that capability. But the thing you have to be careful with right now is something we identified actually in the Evolutionary Architecture book called the last 10% trap. This is something that we developed many years ago when I used to work for a company that built applications for clients, and one of the platforms we built things in was Microsoft Access. And we eventually shut down that part of the business because we realized that every Access project started as a booming success and ended in total failure. And we wanted to understand why that kept happening over and over again. And we codified this as what we call the last 10% trap. And here's what it is. So the last 10% trap says if you take into account all that the user wants, the totality of what the user wants, and using a tool like Access, about 80% of what they want is really fast and easy. The next 10% is possible but difficult. Because now you're trying to do something the tool wasn't really designed to do, but you can kind of bend it and hack it and find a clever workaround and finally get that to work. The problem, though, is that last 10% is impossible. And users always want 100% of what they want, and they're never satisfied with less. This may answer the question for some of you of whatever happened to all the 4GLs. 15 years ago, these were the tools we would have been talking about at a conference like this. DBase, Paradox, Visual FoxPro, Access, Power Builder. Where are they now? They all suffered from that last 10% trap, and we always go back to general purpose languages and general purpose architectural styles, because they're the only ones that are flexible enough to build things that can survive the real world. And right now, much of the serverless world is in that last 10% trap. I don't know that it will always be there, but you just see the things that happen. It's like, oh, it was brilliant. I prototyped this thing, it was awesome, but then when I tried to put it in production, I had to create another Lambda to ping this one to keep the startup time from it, and all these little hacks and other things that just reek of the 4GL stuff that we had to do back in the day. So it's worth keeping an eye on, but it's not a unique architectural style yet. It's just a deployment pattern. So those are all of the technically partitioned architectures. Let's talk about the domain partitioned architectures. And there's a monolithic version of this. Simon Brown is a well-known architect in the UK that talks about the modular monolith, which is still a monolithic architecture, but the separation here is around domain concepts rather than technical capability. So this yellow box here would be something like a catalog checkout. Now, it may actually have layers inside it for persistence, etc., but the partitioning at the top level is around domains inspired by domain-driven design. And this, of course, is driven by domain-driven design and a lot of the other things that we've learned about modern architectures, but this has basically the same physical characteristics as a modular monolith. It's just partitioned a different way. And notice would make this much more suitable for migration into a microservice architecture, which is also partitioned that same way. This is also a distributed architecture where all of these are distributed as individual pieces. Microservices give you protocol-aware heterogeneous interoperability. Now remember, our friend orchestration-driven SOA was protocol-agnostic heterogeneous interoperability. This is one less than that, because you tend not to build big giant coupling points like integration hubs in microservices, and so a common convention in this architecture is, well, these things know what protocol to call each other with. We'll standardize on that versus building a big giant mechanism to handle that. This, of course, the components here are very small, inspired by domain-driven design, and of course inspired by this idea of bounded context from domain-driven design. One of the things that people struggle with in microservices is which are the right size for my microservice. I actually did a much longer talk about this a couple of days ago, or yesterday, I guess. But purpose is one of those for finding the right size, looking at a domain exercise to look at where the workflows are. But things like operational concerns, transactionality may be something that causes you to bundle several back together. One of the anti-patterns we see are people breaking them down too small and then trying to wire them back together with distributed transactions, which are almost impossible to get right. So you're better off just bundling them back together and putting the transaction inside the service boundary. Too much orchestration choreography, which is often one of the Achilles heels of this architecture. If you break things down too small into tiny little microservices, but then they need to coordinate with each other to do work, the communication latency and overhead will kill you from a performance standpoint, because any HTTP call or message queue call is an order of magnitude slower than an internal method call in process. And so too much choreography is also a driver for bundling these things back together. But it's important to remember here, the word microservice is a label. It's not a description, and it's not a commandment that you're supposed to make these things arbitrarily small. And so finding that right level is sometimes tricky. I mentioned transactionality you want to try to avoid in this architecture as much as possible, and a lot of the patterns in this world are ways around that. The overriding philosophy here, of course, is the bounded context idea from domain-driven design, and that really informs this architecture, and especially the inclusion of the data within the service boundary, which of course makes transactions part of your architectural decision-making within this architecture. One of the clever tricks, or one of the many clever tricks you use in this architecture, is figuring out how to get data to who needs to see it. So there's a lot of concern about who writes and updates data versus who can see it. And so caching and replication and other techniques are often used in this architecture to solve that problem. You often see an API layer written in these architectures. An API layer is optional. It's never an enterprise service bus. It's basically a proxy to keep you from wiring the details of your architecture to individual services, because you often have things like service discovery that's handling instancing for your services. So you want some mechanism to handle the instancing for you, not wiring directly to calls to services. You can also have different API views of different parts of the world. You can also use a microkernel for that. This may also be a bit of indirection from a user interface. If you have like a single-page JavaScript application, you may want to put a level of indirection in between those, between your microservices. And one of the common tuning techniques in this architecture is to use events, particularly in a broker topology style, to improve performance, because performance often lags, as I mentioned, in this architecture. So the drivers for this architecture: modularity, agility, fault tolerance, testability, deployability, all of these things are things that we value a lot in modern architectures, and this does all of those things fairly well. And as you'll notice, this gets really high scores here, except for overall cost, which is 1 star, which means very expensive to implement, and simplicity, which is also really poor. It's ironic because the individual services are very simple, but then you aggregate them all together and things get very complex. The last of these I want to talk about is a hybrid, an intentional hybrid called a service-based architecture, which is the basic goals of microservices, but a little less philosophically rigid about it. And these basically differ in 3 key ways. They're still domain-centric architectures, but they differ in these 3 factors: service granularity, database scope, and deployment pipeline. Whereas in a microservice, you're trying to get down to a service or bounded context per service boundary. In a service-based architecture, you're just trying to create sort of larger domain-centric services, but without the level of granularity you get in microservices, which makes this a much better target for migration from a monolith into microservices. It's hard to break things down to that small in microservices, so breaking them down to bigger chunks is easier, which will often be better performance because you're not doing as much at the network level, but development's going to be more complex, probably more robust because you have fewer moving parts, but testing is more complicated. It's still domain-centric, but things like deployment pipelines become more complicated here. Probably the most difficult thing, particularly in migrations and microservices, is breaking the data down to this degree. And so a service-based architecture says, okay, don't even bother with that. Let's just use a single relational database. We know the database has been a big giant coupling point forever, and we're accustomed to it as a big giant coupling point, so let's just live with it as a big giant coupling point, or maybe 1 or 2, but not to the level that you see typically in microservices. So again, this may give you much higher performance, and it may not even be feasible for you to break your database apart like that, but higher coupling because of the database, and now schema changes can, of course, break your architecture. This is a really good hybrid that scores in the middle ground of a lot of these, and this is in fact one of our favorite targets for taking a monolith and getting to a distributed architecture without going all the way to microservices. So the last two I want to talk about here briefly are domain-specific architectures. All the ones I've been talking about are general purpose because they're trying to achieve a balance between these architecture characteristics. But what if you just took one or two architecture characteristics and wanted to go crazy with just those to the exclusion of the others? And one of these is a space-based architecture. So let's talk about scalability. So let's say you have this topology, which is basically what Amazon started with. And then good things happen and you get slammed. So what do? You add more web servers. What does that do? It slams your application server. So what do? You add more application servers. What does that do? Well, that slams your database. So what do? You add more database servers. Well, then those get slammed. So what do? You add more. I've run out of places to add stuff. And this is pretty much what Amazon found themselves in, where they called up Oracle and said, we need the bigger version of your database. And they said, no, you got the biggest one we make. Have a good life. Thank you. But it's still not. And so that's where the specialized architecture called a space-based architecture comes in. Because it turns out you can't use a single database and get those levels of scale. So a space-based architecture had a bunch of really intricate parts. This is built on the concept of tuple space in computer science, where the processing unit here is the one that did actual work in this architecture, but there are hundreds or thousands of these running, all managed by this virtualized middleware, where you have a messaging grid that manages the message dispatch and harvesting all the messages, a data grid which manages replication across all the nodes and then sucking things back into a big data replication engine. So there are data readers and writers here that managed all that stuff for you. The processing grid took control of priorities, et cetera, in this architecture. The data replication engine changes that would happen there would flow through the data reader and then get propagated back out into the tuple space. And you could either have a custom data writer here or have each of these write themselves into your single database. It's quite common for parts of this architecture, all the tuple space part to be in cloud and then part of it to be on-prem. You could have, there are all these custom protocols you can make to make this really efficient across a lot of a big memory space. So these are complex enough where you actually need implementations for them. And so this is what Oracle Coherent started life as, was a space-based architecture. And these have mostly turned into big giant caches, which is the way these things act, are big giant caches. But it's really about variable scalability. It's really good for applications that have variable load or inconsistent peaks. It's not great for hardcore relational transactional systems, but it does give you the ability to do things like 10,000 new requests show up within a half a second, and we can still manage that from an architectural standpoint. So this leans heavily on elasticity at the exclusion of a lot else. And the last one I want to talk about very briefly, there's a nice write-up on Martin Fowler's site if you want to dig more into this. This is a fascinating architecture called LMAX that was created for a financial services company. They wanted to see how many transactions a second they could run through a Java VM, and they managed to achieve 6 million transactions a second on a single Java thread. I'd say they were successful. And the real trick to this architecture is the simplicity of the business logic processor. So it was ran in memory, had no framework, so the bytecode was so small that the CPU could cache the bytecode. And they tuned it to get it to that point where it could live in the CPU's cache. And they had lots of instancing of these things running, and they would apply this business logic processor like a shotgun to requests that came in. The real trick to this architecture is this input disruptor. And this architectural component is now in a bunch of high-scale log tools and other tools that need to achieve ridiculous kind of scale like this. What this input disruptor did was receive message, journal it, replicate it into multiple slots, and then unmarshal the data, and then applied that business logic processor to it. It created a circular ring in memory so that you never had to run the garbage collector, and they had 20 million slots for the input buffer. And so when messages would come in, they would get blasted out into a whole bunch of these spots, and then these processors would just chase each other around this ring, and they managed to eventually get this to the point where it could manage 6 million transactions a second. These were idempotent, meaning that you could apply the business logic processor to the same message, but you always got the same result, and you just use one and throw the rest of them away. The output disruptor was a lot simpler, so you only needed 6 million of those because all it really did was marshal the message back and put it back on the queue. So it's a fascinating architecture to look at if you really want to see what it would take. They were part of the people who founded this idea of mechanical sympathy. Really understand the mechanics of how CPUs and bytecode and all those things work if you want to create insanely high performance systems, which that's a great example of. So it's really important to understand this really fancy term, domain architecture isomorphism. What shape is your problem in? And make sure you choose an architecture that matches the shape of your problem. So microkernel is a great example of that. If I have customizability, that's a perfect architecture, but if I don't, then it's a really difficult thing to implement. Understand the philosophy of each of these styles because it allows you to understand when you can bend it without breaking it. Hybrids are everywhere, so almost never do you see one of these pristine styles in the wild, but there are all these different hybrids, and so expect to see those. And be careful to distinguish patterns from tools, which is a hard thing in our world. Understand the architectural pattern first, and then understand how the tool applies to that. It looks like I'm out of time, so thanks very much for coming, and hope you enjoyed it.